Good morning, students. Welcome to Complex Analysis Live Lectures. In this class, we will discuss Cauchy Goursat Theorem, which is one of the main central results of complex analysis. So, in last class, we have seen what is meant by a. We can quickly recall what we have seen in last class due to Cauchy. So, what it says is that if f is analytic, okay, and f dash is continuous, okay, then integration of f of z dz over C, where C is any contour, closed contour, okay, equal to 0 for all closed contours C. Okay, fine. Now, of course, if you want, you take here simple. Okay, then now what we will see is this Goursat is the first one who removed this condition that f dash is continuous and proved that if f is analytic on points and inside that given simple closed contour C, then integration of f of z dz over C is equal to 0. Okay. So before proving that result, we'll start with a lemma which is useful statement. What it says is that if f is analytic at all points of the closed of the you can say region the region are okay, if you want to write closed region are containing all points interior to and uh, on the simple closed contour C. Okay, so you take that region containing interior to C and points of okay on that curve C. Then given any epsilon greater than 0, okay, the region R can be covered by covered by finitely many finitely many squares or partial squares they indexed by you can call it j, which is equal to 1 2 up to n, okay, such that if you take any sub for any square or subsquare, that means for any sub region if you call it, then such that for any sub region j, okay, sub region indexed by j, that means that may be a square or partial square, there exists a point zj in that one such that mod f of z minus f of zj upon z minus zj minus f dash of zj is less than epsilon for all z belongs to that subregion. Okay. If you want, you can call it this as 1 later, this inequality, because we can use it. Okay. For all points belongs to this subregion. Okay. And it is true for every for any subregion. Okay. So what it says, the overall idea is if f is analytic and that closed region, okay, containing these points of C and inside interior to C, then this R can be covered by finitely many squares and partial squares, okay, such that if you take any that square or partial square, there is one point zj satisfying this condition for all points. Okay, here I have to mention for all points z, for all z except except z. That means here z should be different from z. Then only it is valid, right? So that we have to keep in, right? Okay. So proof is not difficult one. It is mainly understanding through visualization or pick. Okay. One can easily check that. Uh, Suppose this is our region R. So first, let me draw C. Suppose assume that this is our C, which is positively oriented. Okay, and this is inside is our R. Okay, whatever R contains points of this and inside. Okay, so this is our R. Now, whatever epsilon you give, for depending on epsilon, the number of squares and partial squares change. Okay, fine. So, what is the meaning of this? So let me draw this here. So this region R can be covered by finitely many squares and partials. How? Obviously, we can take. Let me put this. Understand? Okay. Now draw line parallel lines to x-axis. Okay, and like this. Okay. Then, but whatever distance between two parallel lines, how much is that? So same distance we have to that much distance we have to take vertically also. Okay, so that they will become whatever we have inside, they will become square. While I'm drawing, some parts may look like rectangles, but here if we can draw it properly with proper lines, then it looks like square. Okay, so assume that these are all square, that means equal sides. So how we get equal sides? Draw parallel lines, vertical lines and horizontal lines parallel to x-axis and y-axis, but maintain that whatever distance between two horizontal lines, that same distance should be there between two vertical lines. Then we get square. Okay. Now, what is meant by a partial square? So, if you observe this much part, whatever we are having, okay, this is actually a square, right? But partial square, we consider only this much part. Okay, this much part we will remove. We consider only this. We consider this as our partial square. So this is a partial square, this is a partial square, and whatever we are having inside, complete one, they are full square, or you can call it square. Okay. So if you want, you can write this as partial square. So we consider only the part of that square which belongs to R. That we call it as a partial square. So if we call it now square, means that it is either a square or partial. Okay, we can easily check that. We can cover finitely many using this. Okay, now what is important is, now if you take any square or that partial square, we should able to show that there exists a point satisfying this inequality for all other points in that subregion. Okay. Okay, so that we will prove. So the proof is that easily, clearly R can be covered by squares and partial squares as shown above. Okay. We already explained that above. That means take parallel lines with same distance and so on. So we get. Now we prove this one that take any j, then there exists. Okay. So we prove this by contradiction. Now the proof by contradiction. What is meant by saying that proof by contradiction? Suppose, suppose there exists a sub-region that is either a square or partial square. Okay, J such that no Zj exists satisfying this inequality 1, such that no such Zj exists satisfying satisfying inequality 1. Okay, that means we don't have a point Zj in that particular region satisfying this inequality. Okay, we can call it that, say, uh, say the subregion by, call it sigma 1. Okay, so we have a subregion now sigma 1 where there is no point zj satisfying that inequality. Okay, now how we will do that? This sigma 1, because it is a square or a partial square, will split that square into 4 equal parts. Okay, so so for our understanding, we'll just take this as a square. Same thing is true even if it is a partial square also. Okay, so that means we can divide this now into 4 equal parts. That means 4 squares, smaller square. Okay, this is our sigma 1, right? Now we are dividing this one. Now we can assume that this sigma naught, the 4 squares which are coming from the sigma 1, also does not satisfy this property inequality 1. Okay, one can observe that. How we can write that? Now we can divide sigma 1 into 4 equal square. Okay, such that, and we can also assume that each of this square, okay, is not satisfying this inequality 1. Okay, why? Um, so suppose if all satisfy, so if all this one, this one, this one, this one, this one, if 4 squares satisfy that inequality 1, that means if we take this square, there exists some zj. If there exists, there satisfying that inequality, and if you take this square, it satisfies. If we take this square also, it satisfies. If we take this square also, it satisfies. Suppose if all these 4 squares satisfies the inequality, then going to this one and equally dividing this part into further. That means each square we will divide into 4 equal squares, okay, of the same length. Then, because the problem was with that square, right, and that square we have divided into small 4 equal parts, and if at all there is that in each sub square, small square, if that zj exists, then by dividing each one into smaller parts, okay, of that length, we can observe that this theorem is true, because whatever here, if all those, whichever subregion has a problem, that we have divided into 4, and if all these 4 squares have that inequality 1, holds inequality 1 in each subsquare, then by splitting this one into even smaller parts of that given length, we can make sure that at every subsquare that is satisfied, so we are done. Okay, so that means among these 4 squares, at least one square does not satisfy this property. If every square satisfy this property, then we can, as I explained here, we can make it this mesh into smaller parts such that in each part it satisfy this condition. Okay, you can repeat this statement for wherever subregion not is satisfied. Okay, because there are only finitely many, so after finitely many steps we are done. We are having a small mesh where every square has a part, right? So therefore that contradicts to this one. That means what? We can guarantee that by, so we can divide sigma 1 into 4 equal parts. So one of them, in among those 4 squares, one of them does not satisfy this inequality 1. Okay, so among them, say sigma 2, okay, does not have inequality 1. That means what? That means there does not exist, z j, okay, in sigma 2 satisfying this inequality 1, right? So without loss of generality, we can assume that This is our, whatever we are square, this is our sigma 2. Okay, this entire one is our sigma 1 and this is our sigma 2. Remember, in sigma 1 also inequality 1 is not set, and in sigma 2 also now we got that inequality is not set. Okay, now we can repeat by repeating the same process, by repeating the same process for sigma 2, we get sigma 3 and so on. That means now take this sigma 2 and try to split this sigma 2, divide this sigma 2 into 4 equal parts. Okay, if all these 4 parts satisfy that condition, then by dividing like this we are done. So therefore at least one of them is there which does not satisfy that one, that we will call it as this, we will call it as this inside one, we will call it that as sigma. Okay, so therefore if we repeat, keep on repeating this, hence we get a decreasing sequence sigma 1, okay, which of course contains sigma 2, contains sigma 3, and this is an infinite, because at every stage we are getting one smaller square which does not have that inequality. So split that smaller square into 4 equal parts, 4 smaller squares, keep on doing and select one of them, and so we get a decreasing C. Okay, right? Now you let me draw that sigma 1, sigma 2, sigma 3 and so on one more time, so that we can understand. As I said, this we can always understand better. Okay, so assume this is square. Okay, now I'll select this another square. So I'll try to draw half. Okay, this blue color is sigma 1 and this red color is sigma 2. Okay, let me take another color. Green I'll take. This much is half. Okay, this is our sigma 3, and another half if I take, then this is my sigma 4, and okay, fine. Now, so it is a decreasing sequence you will have to observe that this sigma 1 and sigma 2 have some common phase. This entire thing is sigma 1 is contains sigma 2. Okay, sigma 2 contains sigma 3 and so on. Okay, so if you consider this one horizontally and vertically, I will write, because we are going to apply nested interval theorem two times. One is for horizontally and another is vertically. So if we write horizontally, how this look like? This much is your sigma 1. Okay, this part I am, okay, or you take this part. Okay, in this part, then what is there here is, you can see that this much is your sigma 2. Okay, so this much is your sigma 2, which is common for sigma 1 as well as sigma 2. Then what we have here is green one, which is there here. Okay, so that means this much is common for all, right? Then what we have here is orange. Okay, that much is common for this much. It will keep on decreasing, right? So you have a nested interval theorem, and for this horizontal, if you take, then by okay, so by mm, uh, let me draw this much. This much is your sigma 1. Okay, and this much is your sigma 2. Okay, and this much is our sigma 3, and this much is our sigma 4, and okay, so you can see that you can apply nested interval theorem, and vertically also I will write, so that we can understand what is vertically means what. So vertically here you can see that this is sigma 1 and this much part we have, right? So I can straight away, right? So what we have here is this much is sigma 1, then we have this much, half of that, okay, is sigma 2, then we have here half of that green, right? So this much. Then in that half we have again arrange. Okay, so this much is your sigma 1, then this much is your sigma 2. Okay, and this part whatever we are having is sigma 3, and whatever we are having here is sigma 4. And okay, right. So therefore we can apply nested interval theorem. We will have a common point for this and horizontally, and we have a common point for this vertical, right? So therefore by nested interval theorem, applying one time for horizontally and one time for vertically, there exists a point z naught, you can call it x naught comma y naught, okay, which is common for all these squares. Okay, common, a common point for all sigma I. Okay, so I hope you understood. There exists a z naught which is common for all these square. Okay, fine. Now we got a z naught. Okay, now we got this z naught which is common for all these sigma i's. Now take any neighborhood. So this is the point which we are going to deal with now. This is z naught which is common, right? Now if we take uh, any delta neighborhood, then any delta neighborhood of z minus z naught. Okay, so you take z naught now, we have a common point, then you take neighborhood, delta neighborhood around z naught. So this is your delta. Okay, then if you take this delta neighborhood of z naught, then any delta neighborhood of z naught contains a square or partial square sigma k if, what can be the guess? So each square contains this z naught. So suppose you take this is your square which contains z naught. Okay, then you can observe that if diagonal of length of this diagonal of this square, remember this is a square. Okay, it doesn't look like a square. So extend it. Okay, fine. So if you take the diagonal length of this diagonal, if that is less than this delta, then definitely this square completely lies inside this neighborhood. Contains a square sigma k if length of the diagonal of sigma k is less than delta. So if it is less than delta, then it is there, right? Therefore, this delta neighborhood of z naught, if you take any delta neighborhood of z naught, then we can find a smaller square which is sigma k, which is contained in that. Okay, therefore it contains infinitely many. Therefore this every neighborhood, every delta neighborhood, or you can say every neighborhood, that means you can change any delta for every neighborhood of z naught. Every neighborhood of z naught contains, because in this case this neighborhood contains this square. Okay, you change any delta, you will get another square, and this square contains all points of R. So every neighborhood of z naught contains points of R other than z naught. We don't, because it contains actually infinitely many points, right? That shows that this z naught is a accumulation point of R. Now since our R is closed, because it is a, we have assumed that R is a closed, since R is closed, what we get is that this common point, which is actually a point of R. So it cannot be a boundary or something. So it is actually a point of R, right? Now we have not used so far why this F is analytic. So F is analytic at all points of this belongs to R. So in particular, F is analytic as F is analytic on R. So F is analytic at Z naught alpha. Right? Therefore, what is meant by saying that f is analytic at z naught? That means differentiation of f at z naught exists. That means this implies this, given any epsilon, what we have here is that f of z, because that means you can write here f dash of z naught exists, right? So what is meaning of saying that f dash of z naught exists? That is same as saying that f of z minus f of z naught, okay, upon z minus z naught. And if you take this f dash of z naught, this difference is always less than epsilon for all points z not equal to z naught in that neighborhood, okay, in this neighborhood. Now what is in, you can say, in subregion, right? Whenever mod z minus z naught is less than delta, okay, in subregion for all z minus z naught is less than, right? Now, so this given epsilon, there is some delta satisfying this condition. So for that delta, we can choose. So for this delta, for this delta greater than 0, choose sufficiently large k. What is our k? Is this square? Okay, this one. You can see that becomes smaller and smaller and smaller. Okay, that means diameter will become smaller and smaller. So choose sufficiently large k such that this square or partial square sigma k lies in delta neighborhood of z naught. So if it lies in delta neighborhood of z naught, then this, for every z in this neighborhood it is true. So in particular, this one is also true. So if you want, you can call it this as some star. Then this inequality star is true for sigma k. That means we are able to find z naught which is in sigma k, and for all other z not equal to z naught, we are having this star inequality which is same as inequality 1, which is a contradiction. Then star is true for sigma k, which is a contradiction, because how we have constructed this sigma 1, sigma 2, sigma k, every time we have constructed in such a way that this sigma k, okay, this sigma k does not have that proper zj whichever we are talking about. Is that clear? Sigma 1 we have selected, and then sigma 2 we have selected, sigma 3 we have selected in such a way that if you take any sigma k, there is no point zj satisfying the inequality 1, right? But here we got that for sigma k, we are know that whatever the construction we have for sigma k, this is true, which is not, right? That happened because we have started assuming that, suppose that there is some subregion which does not satisfy that condition. So therefore every subregion in that one satisfies that condition inequal. Okay, this is about lemma, right? Okay, now we will prove the statement. So we can call it Cauchy Goursat theorem. Okay, some say this is silent, so Goursat, you can say Goursa, Goursat, because T is silent. But many times we say Goursat also. So what it says is that if f is analytic, okay, inside and on a simple closed contour C, then integration of f of z over C is 0. Okay, so therefore that means if you see that f is analytic, continuity is dropped, f dash is continuity is dropped here. Okay, fine. So proof is the idea is we want to show that integration of c f of z dz is equal to 0. So the idea is you let any epsilon greater than 0. Okay, then we will show that modulus of this is less than epsilon, or epsilon times some fixed value. So therefore that value will become 0, right? Fine. So we can start with let epsilon greater than 0, and we can have a picture for this one. Same, just like what is the R? Our R, let R be the closed region of uh, of point C and interior to, okay. This, if we take this, then by lemma, lemma R can be covered by finitely many squares, or of course they may involve partial squares depending on how our C is. Okay, finitely many squares such that uh, such that so if you call it squares as the sigma 1, sigma 2, and sigma n, such that for each square, what we have is that condition is there, that mod for each square there exists zj, uh, for each square sigma j there exists zj, okay, such that mod f of z minus f of zj on z minus zj minus f dash of zj is less than epsilon for all z not equal to zj belongs to that square. This square means points on that boundary and inside to that. Okay, it is just like a paper. You can assume. Paper, cut it in square form. Fine. Okay. Now let me take that picture. So here you can see that this is what we did earlier. This is the sigma naught, sigma 1. Okay, all those square. Now mm, so for each of these squares, so whatever square you take, okay, for each of these squares there exists a point, and for remaining all points this inequality is set. Okay, now what we'll do is, for take any square j or sigma j, whatever you call it, okay. So for um, consider a square, okay, you can call it sigma j, okay. Then for this square we will consider the boundary, that we will call it whatever we are having here, that boundary as c, and let cj be the boundary of the square, this square, but that particular square sigma. Okay, so what is meaning of that? If I want to say here, this much is our c, okay, and you can say positively oriented. Okay, this is our particular c, okay, boundary of the square positively oriented, right? Now if you take any point on that cj, then we can, for this we will define, for any point, so for any point z on this cj, that means if you take any point here, okay, we can define delta j of z is a function, new function, which is the value of this one, whatever inside here, when z is not equal to zj, and 0 when z is equal to z. That means this function is f of z minus f of zj upon z minus zj, okay, minus f dash of zj when z is not equal to zj, and 0 when z is equal to, okay. Then we can observe that, then for any point z on this cj, we can see that this is a continuous function. Why? Then delta j is continuous uh, on this square, continuous on square sigma j. Why? Because if you find limit of this one, delta j as z going to this zj, or if you take this limit delta delta j of z as z going to zj, because remaining all points anyhow it is there, only way to check at zj. This is nothing but limit of f of z minus f of zj, z minus f, but this is precisely is same as f dash zj minus f dash of zj. Therefore, this is equal to 0 as delta a. Okay? Therefore, this limit exists and it is equal to evaluated at this point. That's why delta j, this is continuous at every point z belongs to this. If you want, you can call it this C. Okay, continuous on every point on C. Okay, or inside that also it is not a problem. Okay, on Cj, hence on sigma. Okay. Also, we can observe that also modulus of this delta j of z, that is nothing but modulus of this value. Okay, modulus of this value, it is less than for all, right? Yes, belongs to that. Now we will try to find the value of, therefore the integration of this uh, yes, integration of f of z, we will find integration of f of z over cj. What we will find, to find out this, we will try to represent f of z on this cj, we will try to represent f of z here. Okay, so how will represent this f of z? You can write this as, so for any z belongs to this cj, we have f of z is equal to, that means you take z minus zj into f dash of z, then you bring it this here. So f dash of and f of z, first you will get f of zj. Yep. Then what you have here is minus of this, so if you go it here, it will get plus, so plus f dash of zj plus f dash of zj into z minus zj. Okay. Then what is here is z minus zj into delta j of z plus z minus zj into delta j of z. This is our f of z, right? This implies the integration of f of z over cj dz is nothing but integration of this f of, it is this f of zj is independent of z. So here f of zj will come outside 1 times dz over cj plus what else is there, this uh, f of zj to z is there and minus zj is there, so I can write here minus f dash of zj, okay, into f dash of zj into zj, right? That means uh, into uh, yeah, so this is 1 times dj. Okay, Now what is another one is f dash of zj into integration of z dz over cj and plus z minus zj, okay, integration of this delta j z dz over c. Now we can observe that this 1, okay, whatever having 1 here and here, so they are all, they have antiderivative, right? Since 1 and z have antiderivatives, so by yesterday result we know that their integration of this over any closed contour, cj is a closed contour, right? This and similarly z dj, this is equal to 0. So therefore what is remaining is integration of f of z dz over cj is equal to, so this will 0, this is 0, all these three are 0. So what is remaining here is integration of cj of z minus zj into delta j of z into dz. Okay, now uh, this value we want to find, what can be the maximum value and so on. Now again consider this picture. Okay, so for every square we have, right? For every square we have. So let me copy that picture one more time here, another picture, and we will understand. Yes. So if you consider this, so this is one, just like call it C1. Okay, so suppose I will call it, this is my C1, this is my C2, okay, this is my C3, this is C4, C5, and okay, whatever we take. Now you observe that C1 if you take, then this line, whatever we are having, this part is coming for C1 as well as C3. And for C1, it is one direction, and for C3, another direction. Okay. So integrate, when you integrate the function f of z over C1, over this red line, whatever I have underlined, that value is same as minus of the integration of f of z over C3. So those two will get cancelled. That means, and this similarly, this will get cancelled. Similarly, this will get cancelled. So inside part, whatever we are having, all these red lines, whatever I am drawing, they will get cancelled. So what is remaining is when you take the sum, okay. So the sum of the integration of Cj, okay, this z minus zj, or if you want this simply write f of z, not f, okay. What we can observe here is that this integration of Cj f of z dz, where j is from 1 to n, if you take, this is same as, all will get cancelled, only boundary will remain. Okay, so if you go back here, this one, so all this will get cancelled. Okay, remember this is also a part. Okay, this is a, the whatever c is actually part of those squares are partial square. Okay, so what is remaining is only this much, this red color, whatever boundary I am drawing, that is only remaining. Okay, because internal one, it is get cancelled with when you are taking integration of the adjacent square. So therefore this is same as integration of f of z dz over c. I repeat again, because this summation we are taking, so that means you are taking the integration over this c1, c2, c3 and so on, but this internal curve will get cancelled when you do it with c1 as well as c3. Similarly, c2, c4 and so on, so all internal lines will get cancelled. So what is remaining is only this boundary will remain. Okay, that much is remain, which are parts of this cj. Okay, so therefore that this sum of the integration is this. Hence what we got here is that integration of this f of z dz over c, which is summation of f, integration of f of z over cj's, which is summation integration of z minus zj into delta j of dz, okay, over each cj. Okay, so we want to have a maximum value for mod f of z integration of this. So therefore it is like this implies, if you want, we can have modulus of c f of z dz is less than or equal to summation of modulus of integration cj z minus zj delta j of z dz. Okay, we use ML inequality to simplify this. So it is all about now finding the maximum value by using ML inequality. What is the maximum value of this z minus zj into delta j of z? Okay. So for that, now again consider that square. Suppose, remember this is, assume this is a square. Okay, this is square sigma j, right? And we have this cj. This is our c, right? So let assume that this small sj, okay, let sj be the length of square sigma j. Okay, then if you take any point, so this diagonal, you consider this diagonal. Okay, then if you take point, any point z on this cj, suppose this is my z. Okay, then what can you say about here? Hmm? So we have somewhere, because there is a point zj satisfying this, then you can check that the distance of this one is less than length of this diagonal, right? Then mod z minus zj is less than length of the diagonal. What is length of the diagonal? Is less than length of diagonal of this sigma j. Okay, but which is same as, therefore this is mod z minus j. You know, if it is sj and this is sj, then it is square, by Pythagoras theorem, this is root 2, okay, into s, right? This implies mod z minus zj, okay, into modulus of delta j of z. You can see when we define delta j, then modulus of delta j is less than z, is less than epsilon. Okay, so therefore this is less than root 2 into epsilon into, okay, this is true for all z belong to c, right? Fine, of course this is true. Then now what can you say about, so this inside one maximum value we got. Now we want, what can you say about length of this cj? See, the length of cj, if it is a square, then it is length of cj is exactly 4 times cj. We can write, if this sigma, if sigma j is a square, if sigma j is a square, then length of this cj is exactly 4 times this sj. Okay, now assume that our square given is a partial square. That means, let me write just like square. Okay, so suppose assume that our curve is, right, this is our sigma j. Then at that time we can complete this square. Okay, then we can guarantee that length of this, whatever we are having, this cj, so this is our c, our cj is coming here, here and here. Okay, you can easily check that if sigma j is a partial square, okay, then also length of cj is less than or equal to 4 times sj plus this part, whatever we are having here. So that we can call it as lj, where lj is a length of part of this uh, curve, whatever c we have, part of length of c. So length of, we can write instead of length of is a part of l of, that means length of that curve. Okay, a portion of that. That means we are talking about, say, something like this part. Okay, right. So in any case, what we can observe that, so in any case, what we can write here is length of that cj, no matter whether it is a square or partial square, is always less than or equal to 4 times sj plus l, right? So therefore the modulus of integration of this z minus zj into delta j of z dz over Cj. This is less than or equal to m times L, where m is this length, which is 4 times Sj plus Lj into that maximum value of that function, which is here, root 2 into epsilon, root 2 epsilon. Okay. So therefore, therefore the modulus of integration of C of this f of z dz is less than or equal to summation of these things. So this is less than or equal to summation of 4 times plus Lj into root 2 epsilon times Sj, where J is from 1 to n. Okay. Now we want to simplify this. Somehow we should get rid of these Sj's. That means small squares. We should get rid of them. For that, again you come to this picture. Okay. What we are doing is we are taking a bigger square, this one, whose length is S. Okay. Such a way that this contains entire curve, this squares and square. Okay. So remember, the way we are taking this square in such a way that it contains not only C, it also contains squares and the entire partial square also. Okay, that means the part whatever we are having here, this part, we also make sure that the extra region what we are considering, that is also inside this bigger square. Okay, so that is the idea. Now, now choose a bigger square. Okay, with length of side S. Okay, such that C, okay, and each small square, also partial square, okay, lie in this lies in this square. Okay, so we are selecting such square. It is always possible because we have only finitely many squares and partial squares, so we can select a length which is maximum of such things, then it is always possible. Then what we can observe here is that if this is the case, then each Sj, which is length, is less than or equal to this S. Okay, and area of this one is less than or equal to area. So therefore, by considering this, therefore modulus of integration of C f of z dz. Now here one thing we can do, this one we can write here is less than or equal to the here, no matter what Lj you take, the Lj is a part of length of that Cj. Okay, that we can write length of Cj, which is by L. Okay, so therefore this part, this Lj we can replace by L. That means this we can write summation j is equal to 4 Sj plus L into root 2 into epsilon into S. Okay, clearly now this each Sj also will replace by this S, so that we this right hand side we don't have. Therefore integration of this modulus of integration of f of z d over c is less than or equal to summation j is equal to 1 to n, this root 2 epsilon I can write here, and each Sj is less than S. Okay, and similarly 4 times S plus L, because the way we have selected square, this is positive. Okay, therefore what we will have here is each one uh, n we will get extra, right? So let me simplify this further. Let me write first. This one is we can bring this to root 2 epsilon, we can bring, then summation j is equal to 1 to n 4 Sj square, okay, plus summation j is equal to 1 to n root 2 epsilon and L times S. Okay, that is what is here. Now this we can replace this by root 2 epsilon into 4 will come outside. Okay, summation of sj square, that means sum of the areas. So if you observe here, whatever we are having this is area, this is area, this is area, and we are taking sum of those areas, which is clearly less than or equal to area of this bigger square, which is s square. Therefore this one we can replace by s square, okay, plus root 2 epsilon. Similarly, this length of the sum of the sides is less than, length of the sides is less than s. Okay, therefore what we are having, this value is actually equal to root 2 epsilon. Okay, root 2 epsilon and s we can take, then it is 4s plus l. Okay, which is clearly s is a fixed length, l is a fixed length, epsilon is any arbitrary, right? So since epsilon greater than 0 is arbitrary, so what we have here is, and whatever terms remaining is there is a fixed amount. By taking epsilon very small, what we get is that integration of c f of z dz is equal to 0, because this right hand side is depending on epsilon, remaining all values are fixed. So by taking epsilon very small value, what we can make sure that this tends to, okay, that proves that if f is analytic, then integration of f of z over c is 0 for every simple closed. Okay, this is the Cauchy Goursat theorem. Okay, so it is not a difficult one, even though theorem looks, proof looks little bigger, but what we have to understand is we are dealing every time we will partition and we will take these squares and we'll deal with that particular square, okay, by considering boundary of that square cg. Therefore we can notice that integration of f over c is same as sum of integration of f over cj's. Okay, then we will use ml inequality to simplify that particular value, and how we can simplify the right hand side, so that we can make sure that right hand side is only depending on epsilon times some scalar. By making epsilon sufficiently small, we will get that integration of f of z dz is equal to 0. Okay, fine. So we'll stop here. In next class we'll see what is meant by multi-connected domains or simply connected domain. Okay? And how this Cauchy Goursat theorem is also true for such domain. Okay, fine. We'll stop.